So welcome back everyone. Today we tackle partial fraction expansion. So in algebra we usually pick a lot of fraction and we combine them all together using common denominator. Now we have to go back. So we have to get our chunky fraction and divide them in just tiny little pieces that we can integrate. Okay? And this technique won't be just helpful here in Calc 2 to do integrals, but also in advanced analysis, in differential equations, and in complex analysis. So we are going to find it everywhere, basically, in math, and it's going to be also really helpful in engineering study. So we're going to use a little trick, which is called the cover-up method, to skip all the boring algebra when it's possible, okay? And I'm going to also give you other tips and tricks on the way. So let's start. First exercise for today is going to be the definite integral from 3 to 4 of 1 over x squared minus 1. First things first, we want to understand how we can simplify this fraction. And to do that, we are going to use the partial fraction method. And in particular, we are going to use the cover-up method to simplify all the algebra. So let's focus on the fraction. So 1 over x squared minus 1. As a first step, I want to decompose the denominator. This decomposition is pretty easy. This is the difference of 2 squares. So I'm going to get that this fraction can be rewritten as 1 over x minus 1 times x plus 1. And now I'm going to look at two fractions now of the form a over x minus 1 plus b over x plus 1. Okay, so I'll take each factor of the denominator. There is no power here, so the power is only 1 on both sides. And then I rewrite these two fractions like this. Great. Now, how can I find a? So notice that a is seated on top x minus 1. And the root of x minus 1 is x equal to 1. What's the root? Are the values of x such that this denominator is exactly equal to 0. Therefore, in this case, x is equal to 1. Great, so what I do, I'm going to cover the term x minus 1 on the left-hand side. I'm going to cover like this, and then I'm going to plug 1 into whatever is left here, and that's going to be the value of a, which means that for us, a is going to be equal to 1 over 1 plus 1, which is 2, and that's it. Now, how can I find b? Well, for b, I can do the same. So I'm going to have that b is equal to what? Well, b sits on top x plus 1. The root of x plus 1 is x equal to negative 1, which means that on the left-hand side, what I do, I cover up x plus 1, and then I plug in x equal negative 1 in whatever is left on the left-hand side, which means that for us, b is going to be equal to 1 over negative 1 minus 1 is negative 2, so it's negative 2, which is equal to negative 1/2. What did we learn from this? Well, we learned that 1 over x squared minus 1 is equal to 1 over 2 x minus 1 minus 1 over 2 x plus 1. And now we're going to use this knowledge to compute the initial integral. So the integral is the integral from 3 to 4 of 1 over x squared minus 1 dx. And from the partial fraction, we figured out that this is going to be equal to the integral from 3 to 4 of 1 over 2 x minus 1 minus 1 over 2 x plus 1 dx. To simplify this a little bit, we can factor the 1 over 2 in both terms, so this is going to be equal to 1 over 2, the integral from 3 to 4 of 1 over x minus 1 minus 1 over x plus 1. And now I know how to integrate these terms. That's easy. It's going to be equal to 1 over 2, the evaluation of the log of the modulus of x minus 1, which is just the integral of the first term minus the log of the modulus of x plus 1, which is the integral of the second term, and I have to evaluate this between 3 and 4. Let's simplify a little bit this expression further. So this is going to be equal to 1 over 2 times the evaluation. And now here we have a subtraction. So I have to use the property of the log to rewrite this as the log of the modulus of x minus 1 divided by the modulus of x plus 1, evaluated between 3 and 4. And now I can just plug in. This is going to be equal to 1/2. The log, so when x equal to 4, I get 3 over 5 minus the log of 2 over 4. I can simplify this a little bit. So this is 1 and a 2, which means that I can rewrite all of these as 1/2 the log, and now I have to divide 3 over 5 by 1/2, which means I have just to multiply by 2. This is the log of 6 over 5. And that's it. Second integral of the day, x over x minus 2 times x squared minus 4x plus 3. So, as you can see, the denominator is not fully decomposed, and in order to apply partial fraction, we need the denominator to be fully decomposed. So, first things first, let's do the decomposition. So, to decompose x squared minus 4x plus 3, we look for two numbers, p and q, such that p times q is equal to 3, and p plus q is equal to -4. So their product is equal to the constant term, and their sum is equal to the coefficient of x. So these two numbers, what they can be? Well, in order to have product 3, I can have p equal to 1, for example, and q equal to 3. But then their sum will not make -4. So this one is not good. But then one can think, okay, now this is not good. Let's try with p equal to -1 now, and q equal to -3. And now I'm in luck, because now their sum is exactly -4. Given these two numbers, I can rewrite my polynomial as x plus p times x plus q, which in our case means that the two factors are x minus 1 and x minus 3. So given this, we can rewrite our first integral as the integral of x over x minus 2 times x minus 1 times x minus 3. Perfect. And now we can use partial fraction to solve this problem. And how you do it? Well, as always, we're going to use the usual cover-up method. First, let's focus on the partial fraction and then on the integration. So we rewrite the integrand, so x over x minus 2 times x minus 1 times x minus 3 equal. So it's going to be a over x minus 2 plus b over x minus 1 plus c over x minus 3. And again, we use the cover-up method. So what do? Well, we know that a is going to be equal to what? Well, it's going to be equal to, since a sits over x minus 2, we can cover on the left-hand side x minus 2. So we cover it like this. Well, and now we can just plug x equal to 2 inside this fraction here, and we get 2 over 2 minus 1 is 1, 2 minus 3 is -1, so this is -2. Perfect. Now let's erase back the fraction that we had before, and now we know that b is going to be the same things, right? So we cover up whatever b sits on top. B sits on top x minus 1, so we cover up here x minus 1. And then we plug into the root of x minus 1, which is 1. So b is going to be equal to 1 over 1 minus 2 is negative 1. 1 minus 3 is negative 2. So this one is equal to 1/2. And finally, same things with c. So again, we erase whatever we covered before, and c now is going to be equal to what? Well, c sits on top x minus 3, which means that we can cover here x minus 3, and plug into 3 in the remaining part of the fraction, which means that c is equal to 3 over 3 minus 2 is 1, 3 minus 1 is 2, is equal to 3 over 2. Perfect. So now, after all of these, we discover that we can rewrite our integral as, so the starting integral, equal to the integral of a over x minus 2, so which is minus 2 over x minus 2, plus b, so which is 1/2, times x minus 1, 1 over x minus 1, plus c, which is 3 over 2, times 1 over x over 3, x minus 3, dx. And now I can compute all of these integrals directly. They are just going to be logarithmic terms. So it's going to be equal to negative 2 times the log of the modulus of x minus 2, plus 1 over 2 the log of the modulus of x minus 1, plus 3 over 2 the log of the modulus of x minus 3, plus a constant. Now an integral with repeated factor. We're integrating 1 over x minus 1 times x plus 1 squared. And it's different from before because usually we always have linear terms. Instead, in this case, we have this square. That makes things slightly more complicated, and we have to make a different guess for the partial fraction expansion. In particular, what we are going to do, well, we are going to make this following guess for the partial fraction. We're going to say that 1 over x minus 1 times x plus 1 squared, this one should be equal to some a over x minus 1. So again, we take the linear term, plus b over x plus 1. Okay, now no square for the first case. And then to account for the square, we add another c over x plus 1 squared. Okay? And now we cannot use directly the cover-up method, but something close enough. In particular, we know that a is going to be equal, thanks to the cover-up method, this in this case doesn't change at all. So we cover, again, whatever is the denominator of a. So we cover x minus 1 over there. And then we just plug the root of x minus 1 in the remaining part of the fraction. In this case, x is equal to 1. So a is equal to 1 over 1 plus 1 squared, which is equal to 1 over 4. Great. So now we can erase this part. And then we can also compute c using this cover-up method. In particular, for c is going to be equal to what? Well, c now is seated on top x plus 1 squared. Okay? So on the left-hand side, we are going to cover x plus 1 squared. Okay, so we are going to cover this up. And then we are going to plug again the root of x plus 1. And the root of x plus 1 is x equal to negative 1. So c is equal to 1 over negative 1, which is negative 1 over 2. Great. Now, for b, the situation is slightly different. What does it mean? It means that b, we cannot compute it directly using the cover-up method, but what we are going to do, we are going to try to plug a simple value of x on both sides of the equation, and then we are going to get an equation only for b that we can easily solve. For example, what we can do, we can plug x equal to 0 on the left and on the right side, and what do we get? We get 1 over negative 1 times 1 plus 1, which is, 1 plus 0, which is 1, equal to a over -1 plus b plus c. And now we know that a is equal to 1/4 and c is -1/2, which means that this equation reads -1 equal to 1/4 -1/4 plus b -1/2. That I can rearrange all of these and I get that b is equal to -1/4. Perfect. So now I found a, b, and c here. So I can rewrite my initial integral using this partial fraction expansion, which means that I'm looking for the integral of 1 over x minus 1 times x plus 1 squared. And this is equal to what? So it's equal to the integral of a, which was 1/4, 1 over x minus 1, plus b, which is -1/4, -1/4, 1 over x plus 1, and c was equal to -1/2, so we had -1/2, 1 over x plus 1 squared dx. And now all of these can be done immediately, all these integrals. In particular, we get that I have 1/4 the log of the modulus of x minus 1 minus 1/4 the log of the modulus of x plus 1. And now the last one, we have to do a little change of variable in our head, x plus 1 equal to t, and then we can integrate it, which means that we get plus 1/2 1 over x plus 1 plus a constant. Okay, so how do you compute this integral pretty fast? So you remember that x plus 1 squared, the denominator, the primitive should look something like this, and then you check, right? So you take the derivative of each of these objects. It's going to be -1 over x plus 1 squared. So here you want a negative side, so here you must take a plus sign. Okay, and that's it. For the last exercise of today, we are going to do the integral of 1 over 2 times x squared plus 1 times x minus 1. So this integral is different from the other because we have this term of x squared plus 1 that it cannot be reduced, okay? So we have to keep this quadratic term into the partial fraction expansion, and it's going to make things a little bit more complicated, but still, it's just algebra, okay? So don't get scared about it. So first things first, let's try to do this partial fraction. So we want to find an expansion for 1 over 2 x squared plus 1 times x minus 1 equal to what? So ax plus b over x squared plus 1. And why we do it? Well, because we have this term, which is square terms. So in the numerator, we have to keep something linear. So we have an x and a b part, okay? Plus c over x minus 1, okay? So for c, to compute c, we can still use the cover-up method. How we do it? Well, as always, so c sits on top x minus 1, which means that I have to erase x minus 1 from the left-hand side, and then plug into x equal to 1 in whatever remains. So I have 1 over 2 times 1 plus 1, which is 4, which is 2. So this is 1 over 4, which means that c is equal to 1 over 4. Okay? So this is great for the first part, but now we have also to compute a and b. And how we do it? Well, there is not a general technique, but there is a general idea. First things first, what do we do? So we know that this equation has to be true for all values of x, okay? So in particular, we can decide to pick two values that are particularly useful. For example, x equal to 0. Okay, so let's consider this equation when x is equal to 0. What does it become? So this becomes 1 over 2 times 1 times 0 minus 1 is negative 1 equal to a times 0. Oh, that's 0. So b over 0 plus 1 is 1 plus c over negative 1, but c we know is equal to 1/4, so this is all minus 1 over 4. Okay, so we got an equation only for b, and it looks pretty simple too. Indeed, what we have is that on the left hand side, this becomes negative 1 over 2 equal to b minus 1/4, which means that b is equal to negative 1/4. Okay, that's great. So we found b and c. The last one to find is a. So how do we find it? Well, again, there is not a general technique, but it's a general idea. Now, we put two values, basically, x equal to 1 and x equal to 0. That's what we used. We can use a third values of x, for example, x equal to negative 1. So what we do, we just plug into x equal to negative 1 in the previous expression. And what do we get? Well, on the left-hand side, when we plug into x equal to negative 1, we get 1 over 2 times minus 1 squared is still 1, so 1 over 2 times minus 2, so negative 1 over 8. So the left-hand side becomes negative 1 over 8. The right-hand side, so what do we have? We have a times x. X is equal to negative 1, so this is b minus a over x squared plus 1. So b minus a over x squared plus 1. X squared is negative 1 squared is 1, so 1 plus 1, this is 2. And finally, we have c divided by x minus 1 for x equal to negative 1, so this is c over negative 2. And c is equal to 1/4, so this is minus 1 over 8. We have computed b before, so this equation becomes an equation only for a. So we get a negative 1 over 8 on the left hand side equal to b over 2, which is negative 1 over 8 again, minus a over 2 minus 1 over 8. So 1 over 8 and 1 over 8 simplifies, which means that a has to be equal to negative 1/4. Perfect. So we found a, b, and c. So we can rewrite our integral using this expansion now. So the starting integral was the integral of 1 over 2 x squared plus 1 times x minus 1. And we discovered that it is equal to the integral of what? So a is negative 1/4 and b is negative 1/4 too. So it's going to be negative 1 over 4 x plus 1 divided by x squared plus 1. And please do not simplify these two because they are different, okay? And then c, we discovered before, it was 1/4, so plus 1 over 4 times x minus 1 dx. Okay, now this integral is doable. It's a bit more complicated than usual, but it's still doable. So first things first, the good idea is to always split this fraction. So you split it into two parts. So this is equal to minus 1 over 4 times the integral of x over x squared plus 1 plus 1 over x squared plus 1 plus 1 over x minus 1, okay, dx. There is a minus sign here, sorry. because I factor the 1 over 4, the negative 1 over 4 up in front. Okay? And now these three integrals, I can do them immediately, all of them. Indeed, so I always have negative 1 over 4 times what? So x over x squared plus 1, this is the log of x squared plus 1 over 2. You can check this. Indeed, when you take the derivative of this object, you get 1 over x squared plus 1, it's here, times the derivative of the internal function, which is 2x, so you get the x, but then you have to get rid of the 2 up in front, so you have to divide by 2, and that's why there's a 2 here. The second term is just the arctangent of x, so this is the arctangent of x. And the last one is just a logarithmic term, so this is negative the log of x minus 1, plus a constant. And that's it, guys. So I hope I convinced you that the cover-up method is your best friend when you have to do partial fraction. Use it for all the initial factor, and use the trick of plugging in 0 when you deal with quadratic decomposition. Okay? And as always, you will find a breakdown of the method in my repository, and the link is down below. I'll see you next week, guys.